All right, so we're going to go ahead and get started. So welcome to another special entry of the Thinking Out Loud series. And for those of you who may have heard about this for the first time, this is really the brainchild of Professor Chris Rose here from the School of Engineering, whereby there's this question of individuals who muse on the deep things that go bump in the night and do weird stuff in the daytime. And it's meant to be not just musings and things that have to do with really deep concepts that could be in science and engineering as a whole, but people who can effectively communicate across disciplines. Right, so that's also basically a very special thing. So hence the thinking out loud piece. Today we have with us Professor Joel Ducoste. He's coming from North Carolina State University. He's a professor and associate dean for faculty advancement in civil construction and environmental engineering department. So he's an environmental engineer, I think it's safe to say. And I'll tell you a little bit about his background. So he basically went to school earlier than I did. And but we went to the same place. So I was a faculty in Illinois, and we found out that we have the Illinois-Urbana-Champaign connection because we were just talking about corn. And so that's pretty cool. That's what you talk about, Illinois Champaign. He's a board-certified environmental engineering member with the American Academy of Environmental Engineers and Scientists. He's nationally and internationally recognized expert in modeling water and wastewater treatment processes using CFD or computational fluid dynamics. He has a broad array of research expertise that include physical modeling, physical chemical processes and waste treatment, CFD or computational fluid modeling, chemical and UV disinfection, advanced oxidation, energy recovery from wastewater. So it's a very, very broad range of expertise. He's received numerous awards, including the NSF Career Award, Fulbright Fellowship, visiting professorship at Ghent University. He's an elected fellow of the Water Environmental Federation and the Fair Distinguished Engineering Educator Medal. He's also served on a few boards, including the EPA Science Advisory Boards, as well as the EPA Board of Scientific Counselors Safe and Sustainable Water Resources Committee. So it's really a true honor to have him here. And I think before he takes the stage, we'll have Professor Rose say a couple of words.
Thank you.
Yep, thank you.
Thanks, Mike. Okay, so, everybody, so first off, how many recidivists do we have here? How many folks have been to a previous Thinking Out Loud? Right, so, a whole new crew, basically. So this is a presidential series. It's funded by Chris Paxson. And it's everything that Kimani said. My job here is, you have your programs, right? And you can look and see who Joel is. And that's not what I'm here for. That's not what I do. Plus, I don't like puffery. We shouldn't puff. So what I'm going to do is I'm going to puff in a slightly different way and, embarrass them a little bit. You have to do that. So, assuming this actually works, okay, we'll see. You have to turn it on. No, that's off. It buzzed at me. It was working. All right. Hello? Help. Okay. The laser works. Ah, magic.
Excellent. Yeah. All right. If you'll just stay towards the microphone.
Got it. Okay. Okay, so let's see. Do I just click?
Yes.
Okay, so I just click and you can all see me. All right, so I clicked. I'm going to click again. Let's try rolling. Next. We'll just have to do that. So the first thing is that, he's a civil engineer. And he's a civil engineer, and he seems to have disappeared. So he's a civil engineer, and back in my day, this is kind of what civil engineers did. And these are all pictures in New York. There's a bridge, right? I have a bone to pick here, and it actually is germane to what Joel does. This is a park, right? Looks like a park, right? No, it's a sewage plant, damn it. I used to live, this is in Harlem, and I used to live, somewhere up and behind there. And they said, we're giving you a park. And we were so excited. But it was actually a sewage plant. So, these are the sorts of things when you think about civil engineers, they build the public works and things like that. Well, kind of needless to say, next again. Let's just look at some of Joel's selected topics. So, here's one, the effects of UVC and disinfection on N95 and KN95 face piece respirator reuse. Optimization of waste stabilization, pond design for developing nations using computational fluid dynamics. And good modeling practice in applying computational fluid dynamics in wastewater treatment plant modeling. So, and there are a couple of other titles that I wanted to include just to kind of not wow you, but like, can you get more obtuse with the title, okay? So I'm going to translate these three. These are the simpler ones that I could actually translate. So the first one is, will you catch COVID from a reused mask? I mean, that's the very simple first one. The second one is, people will die if you, do this off-brand wastewater treatment, building treatment. And then the last one is, and this is really where it gets kind of interesting. If you don't even understand the model you're using, how the heck can you do anything, okay? And this is kind of where Joel comes in and why he's part of this series. We can get any number of really accomplished academics and really good speakers. But what we're looking for here are people that span a number of disciplines and put things together in slightly crazy ways. And they have to be slightly crazy, right? Which Joel is. So please help me welcome the wonderful and superhero. Yeah, no, because that's really, that's who you are, right? And I'll get rid of this now. So thank you, Joel, for coming.
Thank you. Wow. Hello, mic check. 1, 2, 3. Are we good? Yep. Awesome. Well, with an introduction like that, I just don't know if I can even top it. I will do my best, but I appreciate you all coming out. It is a beautiful fall day with opportunities to be outside, but you're in here wanting to listen to this topic. Invisible machines. You see what I mean about invisible machines? Doing all the learning. And really, it's a fear of mine. Probably because I probably watched too much television related to science fiction. And of course, Skynet and all of those kinds of things. You can imagine where things could go wrong, but we're not going to go there. But I will say, images like this give me a little bit of the EBGBs if you're thinking about that we're developing algorithms that are sort of mystical, behind some box, really analyzing the data in all different kinds of ways, more than we can because we can't think in that many dimensions. But it's doing it, and I'm not sure if the learning is happening. Now, let me say, if we have machines that operate like this, where they can think about it and we can have conversations, now it's a very different story. Because obviously with machines that are thinking about some of the problems and exploring it, and then we can chat, that's equivalent to what we do today and what you do with your colleagues at this institution. But I'm going to tell you a little bit about myself to give you an idea of what I'm concerned about in terms of machine learning and this idea of deep learning. So I have to go back to roots where my family is from Haitian descent. I was born in Haiti. I came to the United States, to that place where he pointed out in New York City at the age of 3. And at that time, it was for greener pastures. My parents wanted a better life, and they wanted to make sure that I had every opportunity to be successful. So what did my father see in me? This is obviously an image of me a long time ago. You can tell by the old photograph, that they see the game changer of the future. But something went tragically wrong along the way, where they had to send me to a military camp, where I had to learn. You can see that, LaSalle military camp. I kid you not. They sent it to me there as a kid just to straighten me out, to make sure that I was going in the right direction. Well, everything worked out from there. And, I have to always go back, like I said, I enjoy science fiction. My favorite shows were Star Trek and Star Wars. And I really thought at one time that I was of a Vulcan because of my pointy ear, as you can tell that I have one. So I figured I must be that. Of course, another movie came out and I tragically changed direction. So what did my father inspire that really led me to the person I am today? It was this idea of trying to solve problems. Now, he got me involved in trying to fix a lot of things in our house. And he would tell me, well, we need to fix this. I'm not going to tell you how to do it. You're going to have to figure it out. So go through the toolbox and tell me what we need to do to solve this problem. And of course, after bringing him the wrong tool several times, I finally figured it out. But it got me to thinking about problem solving to the point where I started trying to do, board games and things, the puzzles, and I'm still today not good at puzzles, so that wasn't my knack. But he did infuse to me the joy of mathematics. It started out with the simple stuff, if you consider that simple, getting into a little bit more complicated, and of course the calculus that came afterwards, where he couldn't help me, because again, this is a man who didn't have training in mathematics, but he understood it well enough to help me with the simpler stuff. But he was trying to get me involved in doing these kinds of problem solving that I eventually grew to enjoy. So Star Trek, early beginnings. I was thinking when I did my undergraduate, I would go into aerospace engineering and that I would be a part of that whole experience of going out into space. But I felt that the program was a little bit too restrictive. And I ended up thinking like, well, maybe not aerospace, but mechanical. And so again, Star Trek, but now thinking of robotics as a way of doing that. And I did advanced automation to really explore some of that at GE. I will say that during my undergraduate, the research bug took hold because I had opportunities. This is why I always tell students that don't do all of your experience as internships. I would say you do yourself a disservice if you don't do both a internship at a company, but also a research experience, and have both the opportunity to work on solving today's problems and what faculty are trying to solve in future concerns. So I was able to do that as part of my academic training, but the internships, and eventually I went to work for GE Aircraft Engines after I did my master's degree. That was where, in fact, I tell students, you don't have to rush into going to graduate school. If you're still trying to explore, it's an opportunity to really explore your craft. But it was where at GE that I got involved with environmental work and thought, this is what I thought I wanted to do. So even though GE was more concerned about compliance and dealing with, making sure that they can minimize their cost of compliance, I was more concerned about public health protection. Particularly, I was starting to get interested in water and wastewater. And this is an old picture of me. This is me in my lab in a fraction of my setup I was looking at, and I will talk about some of that research later that I set up. I kid you not, at the UIUC website, this is a historical picture. And I'm thinking, wait, this is in 1993. They could have taken this picture in color. Why did they choose black and white? And why am I a part of that? But anyway, that's another discussion. After my doctoral degree, I was not happy with not having practical knowledge in environmental engineering, so I went out to work for CH2M Hill, which is a major consulting firm, just to get that practical experience. It was a pet peeve of mine, but I learned as an undergraduate that it is important to have practical experiences in the classroom. So I did some of that. So because of all of those experiences and my curiosity that was built, I do research in a lot of different areas. Now, the majority of these areas are in environmental, but you can see some things that are cross-disciplinary lines that I was able to collaborate with other faculty in plant biology, looking at biosystems and regulatory metabolic modeling, to the point of working with, more recently, with a biomedical engineer and looking at tissue scaffolding and looking at modeling reactors to develop some of those tissue scaffolding. The commonality of all of that was utilizing data from experiments to develop and validate models. But more importantly, I'm fueled by curiosity. Curiosity that must achieve societal impact, and exploring followed by exploitation. It has served me so well that that's what I try to educate my graduate students, to be excited for years. You know, we go through rough and tumble about times of highs and lows, but what's really going to fuel you if you never lose sight of your lifelong learning? And that's going to be fueled by curiosity. And you'll see that through some of our talks. Okay, so what scares me about machine learning? This is just one definition, right? To allow computers to learn. And I'm thinking to myself, okay, so computers are analyzing, or algorithms are analyzing the data to do that automatically using a number of different methods, right? And depending on the method that's chosen, it should be selected based on what you're trying to understand from that data. And so in their machine learning, and the next thing I'll talk about, deep learning, is used in a number of places. And they argue, presumably it should be in areas where it's not always useful to learn, right? And so I'm thinking to myself, that should never be. Anything that we do should always be in the experience of learning, whether or not it is the machine or the algorithm that first doing the diagnosing of the problem that you're trying to understand. But at the end of the day, there should be a why. Why is it behaving this way? Is it done properly? Does it capture all the nuances? Can it be transferable? There's a lot of questions. In fact, I was having a discussion with a colleague today here, just thinking out loud, you know, what if, and we can have a debate on this, instead of these models which are driven by data, what if we were to build a similar model that was driven by questions? So not only have a whole data stream of all that stuff, but what if we were to put billions of questions alongside of that and let the questions also help almost self-diagnose the problem that you're trying to analyze? Well, anyway, that's for another discussion. The thing that really fears me is that in machine learning, my understanding is that there's a lot of involvement. There's still human in the loop as part of that process. But as algorithms are getting more sophisticated, it's almost to the point where now the concept of deep learning puts humans out of the loop. And I think that should never happen. And I just worry that that is going to be the extent and possible usage of these very sophisticated algorithms. So I can understand why there is a need for that. The problems that we're trying to solve, particularly in environmental, there are multi-physics and multi-scale problems. To capture mechanistically everything to try to solve that is probably way beyond what that computational power is, and probably very hard to validate every little step as part of that chain. So, you know, wanting to use something that's an algorithmic with a data stream that's coming in to capture certain parts of this might be beneficial, that it could be used in combination with some kind of mechanistic model, which is mostly my area that I've done a lot of work in. So, as this nice little cartoon says, you know, these problems are not easy. And people who write the algorithms think that they're going to solve everything. But wow, this problem is really hard. And that really summarizes many of the title. And it's okay, it can be hard, But that's where the learning continues to happen. That's where you might be able to combine with mechanistic models. That's my argument. And people are doing that. I mean, you may be hearing about physics-informed neural networks. That's the opportunity for mechanisms to be incorporated so that these models are at least informed by laws that we understand or concepts mechanistically. So we do this in environmental engineering where a lot of programs, this is a paper that's describing all the machine learning algorithms that are happening within our field. And it's growing, all right, to understanding. And now I could say that some of these interactions that we understand about disinfection and other kinds of disinfection byproducts, we have a pretty good understanding. I can understand the lure of trying to use some of these algorithms. But again, there is a concern about the learning that continues and still should continue in many of these areas where these algorithms are being used. I put this up because for me, if the basic needs, I know this is Maslow's hierarchical theory of human needs, and yes, we can disagree and understand that the hierarchy doesn't have to follow exactly this path. I can understand some of the folks who really study this, that it depends. But the idea that you have basic needs, and once that's been fulfilled, and I'll be upfront, most of my basic needs have been fulfilled. The next level of understanding involves that higher order is that knowledge and that pursuit of learning. And so that's the part I want to make sure that is maintained. Assuming if everything else is okay, that we can get to this part. And then, of course, if we want to continue up this hierarchy, we can. So let me take you to my mechanistic journey. My mechanistic journey started, again, back in graduate school where a question was posed to me. And somebody said, Joe, when we're trying to model aggregation processes, and this is one of those processes is in flocculation to force particles to aggregate so that they're easily to filter out or settle out. Some principles that we expect to work is that if you keep the energy the same in different reactor sizes, you should get the same particle size developed in those tanks. And the data shows that we did not. Why? What was the mechanism that was causing that disparity with scale? What is also the disparity with depending on the mixing that was, if you use a different type of impeller, so this is an axial flow impeller versus a radial flow impeller. If you maintain the same energy, it would dictate that you would get the same particle size distribution and therefore performance in terms of aggregation. We were not. So that was the question that was posed to me. And I went back to fundamentals. We start looking at, well, what are the interactions that are causing these particles to collide to form potentially these aggregates? They had their roots in a turbulent environment where you see all different kinds of length scales. You can imagine them, the little tornadoes that are whizzing around in different parts of the fluids that are causing these fluctuations. And there are these products and fluctuations that are causing stresses that allow these particles to collide. And so the principle says that if I were able to look at the smaller scales and we can map that into energy that is coming into these reactors, we should get the same kinds of interactions from those fluctuations to cause those particles to aggregate as well as possibly to break up. Those same energy would also cause it to break up. So I was tasked with trying to come up with a model. The first thing I did was do the experiments to try to figure out whether or not we can see the evidence that was shown in the literature. I saw that. And then propose a mechanism to say, why did those particles, the aggregation changes with different sizes? And I said, well, that's because depending on the particle size that is being developed, the scales at which these fluctuations are happening may not be dependent on the smallest scales or the energy that's dissipated at the smallest scale. So this may look like a sophisticated equation, but that was an equation that was derived based on fundamentals of where these interactions were happening, and they were happening mostly in the impeller zone. And that's where most of the breakup was happening. And I was saying that breakup was driving these differences between scales, and came up with an equation and modified it this way. So we looked at the data. First, I can tell you, initially, the model didn't work. And I thought, wow, I'm never going to graduate because that's the last part of my thesis. So the way I tell the story is I went away for, I took a week off. I said, I'm just going to walk away from this and then revisit. And I come back and I do a little bit. I said, well, what if I change the code a little bit this way and see if this would make it work? And it started to work. The first thing I did was, well, back then I got an external hard drive. I backed up everything because the last thing I needed was I just solved it and it went poof. But what this shows is a relationship between the number concentration of the particle size over a range of particle size that I measured. And so what I want you to compare is this dashed line, because that was the original model that I created. And what the dashed line shows, as you go from a 5-liter tank to a 560-liter tank, my model was able to track the change in the size distribution as you move with this, which I thought was a perfect explanation for what was happening, was because I captured these larger scales of fluctuations and its impact on the size. Well, that was for the radial flow impeller. When I looked at it from the axial flow impeller, well, I captured the smallest scale, I captured a mid-range, a little bit of error, big error on the large size, which means like I didn't capture this completely. There was something that was missing. And so I went back to the drawing board and I said, well, maybe the equation is right, but maybe it's a multi-mechanism problem. So I said, okay, maybe the breakup is not just on the larger size fluctuating velocity, but it's still also on the smallest scales. And the second equation here that I have was something that was already in the literature, and it was a well-known description of how breakup was going to be a function of fluctuations that are based on the energy dissipation rate. But what I added to it is that, well, what's happening is depending on the size of the particles, and I use the Kolmogorov microscale as a typical size where particles larger than that would be influenced by these larger fluctuating velocity turbulent fluctuations. Particles smaller than that would be associated with this smaller scale fluctuations. When I did that, lo and behold, now look at the solid lines, the model started capturing the exact change all the way through the larger scale, and the same thing went with the other impeller size. And so what that told me was that when people said that they saw these kinds of changes, they saw it only from a large scale event, because at the larger scales, and I scaled this up from 560-liter tank to 1,000 liters, there was no more scale effect. Everything was based on the small scale fluctuations. And so what I also argued in a long time paper is that this kind of event only happens at lab scale. So what people had saw in terms of a scale effect was only a small scale event. At larger scales, it did hold true to the amount of energy that you put in can capture those fluctuations. So this got me into this whole modeling world. And that modeling world led to using computational fluid dynamics and trying to simulate a whole bunch of different things that looked at it as a design tool, a troubleshoot tool, something to better understand process dynamics. And so I model, and I'll talk about UV reactors. And I show these pretty pictures, and I'm saying, I don't have appreciation for modern art, but I think this can go into the Guggenheim. But nonetheless, did stuff with UV reactors, talked about flocculation, and we did more sophisticated models to look at other aspects of flocculation. And more recently, I'm doing simulations with using potentially new methods to, instead of using face mask, What if we all had spot UV light that can protect us and disinfect airstreams before it reaches your face? And these are just new images. And by the way, if you look closely, that's me. That is my image. A student had this kind of scanner and they can do that. And by the way, again, just thinking out loud, I'm trying to work with a researcher that's using, virtual reality to be able to actually be in the simulations to really explore some of the nuances and the things that we're trying to solve. But just some things to think about. All right, so I want to talk about some of these processes a little bit further, just to give you a taste of what I did. UV reactors is a major way that we disinfect in water and wastewater. There were a number of challenges related to UV disinfection. Some of those challenges involve what happens with the flow field as these kinds of systems are put in place with elbows and bends and all kinds of ways to put these kinds of disinfection system in place at these large-scale facilities. And we also did research with LEDs. UV LEDs is up and coming and is starting to be used, and now you can put basically a disinfection in your refrigerator, and there are people are looking at that, and we're using these kinds of tools to do that. One of the biggest challenges in evaluating a UV reactor is that when you're trying to prove that this disinfects a particular microorganism, it only tells you about the overall characteristic of that UV reactor. It doesn't really give you the nuances about the path that these organisms take within that system. And so we wanted to come up with a better way to enumerate what really happens in UV reactors. Let me give you an example. This is a small-scale reactor in our lab, built out of plastic because I was cheap and needed to build a reactor. And if you look at this bouncing blue ball, depending on how the inlet and outlet of that, you'll get different paths that these organisms, if you want to look at that big blue ball as an example of, that goes through this reactor. Here's another one where it has this kind of elbow ahead of it, and you can imagine that because of this path, it starts to forces the flow inside that reactor to rotate. And we did it on purpose, even though you wouldn't design it this way, just to prove a point that you would get a different kind of characteristic performance for that UV reactor. What that means is that depending on the path, imagine in this room you have UV lamps up top and you're not using it to get a suntan, but in other words, this whole room was a disinfection for an airstream, airborne pathogen. Depending on where that path is taken, close to the lamps or farther away from the lamps, you will get a different kind of performance. And so we knew this numerically. We can predict this numerically, but we couldn't get this experimentally. So in order to prove just how those reactors behave, depending on how they are placed in a wastewater treatment or a drinking water treatment plant, we had to come up with an alternative way to measure its performance. So here are pretty diagrams that we can get from modeling, and modeling was very important to the field to help them understand how these reactors behave. The red represents high concentration of microorganisms, places where blue you would expect low concentration or disinfected microorganisms. You don't really lose the microorganisms, they don't disappear, but they are changed and are not able to infect the host if you were to consume it. And you get these beautiful images, and they work out. The industry, places like Jacobs Engineering, uses these tools all the time. But you still couldn't get that dose distribution. And why that's important is because it inherently tells you the efficiency of that reactor, more so than just looking at those models. And so a research team, two research teams, my research I did in collaboration with a colleague that was at Duke, now is at Colorado, and another research team at Purdue came up with a way of using fluorescent microspheres that are, that can change their fluorescence based on exposure to UV light, can be a marker depending on where that path is taken. And so we were successful in doing that, and we used that approach to try to validate. And so for our microspheres, so to speak, our fluorescence would decrease with increasing exposure to UV light. The Purdue team had a microsphere that, with more exposure to UV light, it increased fluorescence. But the change was what we wanted to capture. Both of ours worked. So based on this and looking at these microspheres, we wanted to really evaluate how well those CFD models were doing. And so this is an example of one where we had one kind of elbow and straight pipe comparison just to show how that shift happens. But then when you are comparing against the experiments, there's some differences. Don't get me wrong, it's not perfect, but it was able to show that shift. And so at least it was a way of demonstrating that sometimes you have to develop the methods to measure something that the models already do very well. And that has to go hand in hand to prove whether or not the model that you're doing mimics the reality of that process. So that's UV. So now I want to take you to a totally different area. And now you're looking at this image is like, what the heck is that? And there's more of them. This is the result of you dumping oil and grease down the drain, heading into the sewer lines, forming these hardened deposits. Now, I know you don't purposely do that, but the point is that food service establishments across the United States, they have, processes with cleaning processes that release some of this fog into the sewer lines after going through some separation, but the separation process is not perfect. Our research team, and I started doing this research way back in 2004 at a time when I was approached by a person in the wastewater community and said, Joe, nobody in academia is doing research in this area. And I said, well, it's not exactly the most exciting piece of research. I mean, who would be interested in looking at, these deposits? But I said, I'm a trooper. Let's check it out. And it turns out what this process involves a lot of reactions, which I'll tell you about in a little bit. But I want to tell you how popular this is. These are images of, if you haven't been into the UK, these are images of the jewels that are by the king and queen, right? Very popular, of course. But at one time, they had uncovered this huge mass. They called it a fatberg. And I still kick myself to this day that it was a reporter in the UK that found this huge, I kid you not, 130-ton mass fatberg in their sewer lines. Now, we would never have that in our sewer lines. Our sewer lines are not that big. But anyway, it was so popular that they had a museum exhibit about that fatberg. And I kid you not, for the time period that it was in that museum, it was more popular than the visitation to the jewels of the king and queen. So popular that most recently it is now being considered for Legos. And this is a Lego, and it's still being ranked, but look at the definition of this thing. It's got a vacuum truck with people working down in the sewer system. And this is the simulated fatberg. I mean, I was in love. It's like literally they captured almost all the things that could cause this. They even got the sewer system. I mean, this is wonderful stuff. As soon as it comes out, I'm building the darn thing. Now, I can tell you a lot about this image. It is so wrong in a number of different dimensions. But I imagine they were trying to call these superheroes that are trying to defend against the fatberg. I think they missed the boat. This is really Captain Fogginator, and I think this is the superhero that should be done. If you think faculty don't have fun. All right, so what was the process that we uncovered this? It turns out that process of releasing fog, when it gets broken down, releasing long-chain fatty acids, fats, oils, and grease. I apologize. Fats, oils, and grease. When it is released and it breaks down into in the sewers, it is now long-chain fatty acids that react with calcium to basically be a saponification reaction. And that's what was happening. That's why these solids were so hardened within the sewer collection system. The calcium can come from the wastewater, but it also came from corrosion of concrete structures in it. And we're doing a lot of research to show these kinds of interactions. There's a lot of other processes that are going on, and I'll tell you about some of those. But the bottom line, this was the unknown back in 2004, and some of the research that I've done in collaboration. You know, I wasn't an expert in food scientists, but I worked with food scientists, microbiologists, as well as structural engineers, recognizing some of the contributions with this process too. And this was a multidisciplinary problem. So just to give you one aspect where I can see machine learning and deep learning happening. One of the things I wanted to create was a model that was going to be helpful to the people who are trying to manage the collection system. And in managing the collection system, they need to understand where most of the food service establishments are and that changing landscape. So you can imagine Providence, how many new restaurants came online in over the last 5 or 10 years. That will change the collection system's makeup. And so the model that we were trying to do was to help those pre-treatment coordinators map out what happens when those changes happen. So again, we want to minimize the poor sap that has to go down into the collections system and try to clean it up. This is an actual picture of somebody cleaning up that fatberg in the UK. So I'm glad I'm not that person. But the point is that if we were able to create a model that can look at these collection systems and predict those changes, because they already know where the problems are initially, but they may not know where the future problems are. So utilizing some simplified models that capture the flow dynamics within the sewer collection system. And we did a lot of work in the labs trying to describe how saponification reactions happen. So we took those lessons learned and included some kind of additional process that captures aggregation, some of the process of the actual fogs of deposits being formed, the fats, oil, and grease deposits being formed in the collection system, and then attaching themselves to the sewer wall. And so with those kinds of additions, put it into a mass balance framework within a numerical model, and then, of course, calibrating that. So we looked at 2 different sewer collection systems, one in the Northeast. We couldn't give them by name because everybody was so concerned that what we uncovered would be used against them. So we only call it the Northeast and the Southwest sewer collection system. The hot spots are places where these are locations where the fog deposits are formed in very large quantities. And so we wanted to see how well our model captured some of those hotspots. And it turns out, not too bad. 13 out of the 20 hotspots were predicted with our model. So those are the spots of those hotspots that were predicted. Not predicted by the model. We missed a few of those, which I wasn't surprised. I thought this was pretty good to get that many done. And of course, the model also predicted additional hotspots. In the other collection system, the same thing, but we got 9 out of 14. So it was possible, but there are lots of reasons why we weren't able to predict exactly what's going on. Because the sewer collection system, you can imagine, is very complex. So you've got roots intrusion that happens. You've got pipe sags. These are old aging pipes that are now changing and are not maintaining their infrastructure. You got biological processes, microorganisms that are changing dynamics, as well as debris and, of course, other host of unknown processes. So we're in the process now of working with a team in the UK, because they uncovered the fatberg, but trying to put cameras inside the collection system to monitor how a fatberg growth is happening in real time, and looking at some of these other processes. They they talked about wet naps that just don't degrade. That was something that was removed in our system and we don't allow, but it happens still in the UK, and other kinds of processes. In addition to recent research that we've done related to how the actual deposits attach to the surface is a function of a number of things that is related to the actual concrete material that's being used. And we're making suggestions about those. So all of those things, hopefully with some kind of model that is actually tracking the pattern, we're hoping to develop something. But again, that comes after learning some of these processes and trying to enhance it and explain what's going on. So again, this is ongoing research, again, mostly driven mechanistically, but we are diving into using some data driven based on observations that we see and patterns that we see within the sewer collection system. So the last area that I want to talk about is related to wastewater treatment. And I don't know if many of you know, there are different processes that are involved in wastewater treatment. Suspended solids is removed, organic material, nutrients, pathogenic microorganisms, and including targeted as well as non-targeted compounds. It is something that we try to make sure, again, the overall goal is to make sure that we're putting water back into the environment that is at least as good or if not better than what is related to the natural water system in there. And so there are different unit processes that are used. Those that are related to physical screening of removing of solids, biological breakdown of these contaminants, chemical addition, as well as disinfection for treating that wastewater treatment plant. So this is an image of it. And Chris had already showed an image at a wastewater treatment plant in New York City with a park on top. It's a beautiful park, by the way.
In the winter.
In the winter. So one of the areas that we've done research, and this is just showing a flow diagram of different processes that are used initially to remove solids. You'll see biological processes are usually happening in the secondary treatment. Tertiary, usually talking about disinfection and other kinds of last-minute removal processes. But there's also a lot of work in trying to recover energy from the embedded waste within wastewater, as well as removing solids and then before going out for final disposal. But I want to focus on secondary systems because there are a number of challenges with secondary systems. This is an image of an aerobic system where it's designed to remove contaminants aerobically using microorganisms. And one of the things that we try to do within this reactor is to recirculate some of those microorganisms back into that reactor to maintain its population so that you can break down those contaminants. So you can imagine the settling process is very important. And depending on the types of organisms that are grown, you can get very different kinds of particles that are formed in there. Of course, the biology that is involved in these different organisms compared to very solid circular looking ones are different. And they break down different contaminants. And so in those ones that you saw on the right, which were more circular, those turn out to be very effective in settling out, but they also harbinger very different microorganisms that are targeted to break down certain contaminants. And they can be all done in one type of reactor design. So these aerobic granules is something that is desired for doing breakdown of these contaminants very efficiently. And again, this is just an image of showing that depending on which organism that you find in the different parts, they will take care of different kinds of contaminants. Now, that might seem logical to have something like that, but they are hard to maintain. And so you always have to make sure that the environment that is growing these kinds of granules is conducive to all the different microorganisms that you find within these granules. So one of the things that we wanted to explore is try to understand, well, how are these granules formed? There have been lots of different experiments. Researchers, really, we do have a pretty good understanding of what are the different impacts. But one of the things that we had observed experimentally is that looking at the fluid mechanics and the shearing motion that is happening within inside these reactors, when we saw variable shear, and I'll talk about that, that it seemed to form these granules more often than not, and we wanted to be able to explain that. So we tried using a combination of computational fluid dynamics and cellular automata, which I'll describe in a little bit, to recreate the growth of these granules. And so what we did was, looking at a simplified flow field, using a description of what's happening within these granules that would be formed by microcosms of microorganisms, to see how shearing and the substrates that they are trying to break down that leads to these kinds of granules. So this was just a representation of that boundary. So with time going on, let me just move on a little bit. So here are some of the results just to show about these. The top two images show a condition where we have a low shear environment with low substrate concentration. This is the stuff that the organisms feed on to grow. The bottom image shows a high shear environment with a high substrate concentration. And notice that when you have that low concentration, you form these kinds of open structures, which are not conducive to allowing different kinds of microorganisms to be a part of those granules. In the high shear and high substrate concentration, now you see these very tight granules that are being formed. And so people already knew this and understood this a little bit, but they never really understood that interaction. And what we did in this modeling effort and showed is that, and what they in fact showed experimentally, that sometimes shearing doesn't always influence that granule formation, and you get very low production of these granules. And then high shearing, or I should say high substrate concentrations, now you get all these wonderful granules, but shearing doesn't make it important back then. And how we described a granule formation is looking at this circularity, and this is what we were measuring here in this model. How much we're getting this kind of very circular formation versus this open structure formation. So this was a very nice way of demonstrating what people have shown experimentally. We tried coming up with a generic term to really showcase, is there a dimensionless parameter? And the person that we were working with, a postdoc, showed that, well, what if we took the Thiele modulus, which was a ratio of the reaction rate to the diffusion rate, and rebrand it and take the inverse of that and say, what if we were to capture the maximum substrate that is being transported to these to this flock, divided by the reaction rate that is happening that describes that breakdown. And this is what those equations do. And this is a contour plot of this reverse Thiele modulus. He wanted to come up with a different name. And compare that with shear and substrate concentration. And as you can see here, it sort of tracks very similar to what we saw before in terms of there is a shearing component that really doesn't make a difference in terms of this value of this inverse Thiele modulus. And then there's a section, again, that makes no difference with shear. And one of the things we concluded is that maybe we can use this kind of dimensionless parameter to really dictate how much substrate transport do you really need to have? What's the operational conditions compared to the reaction rate? And what we found was, in even experiments that we did, I'm not going to show that here, that around a ratio of 0.1, we produced the environment that allowed for granule formation. So why I show this, let me move on a little bit just for time. Let's see here. Just to get you an idea. The important thing about this is that there are a number of factors that influence the creation of these granules. We only looked at one aspect of it, shearing and substrate concentration, but all of these have been shown experimentally to influence granule formation. The biggest thing that is of concern is, remember I showed you this image of granules. The whole purpose of forming these granules, besides settling, is to have these different microcosms of microorganisms, to be able to remove different kinds of contaminants, which are the substrates for these microorganisms. This model that we did assumes one type of microorganism. And in fact, right now, we're still trying to figure out how do you decide where the microorganisms go in this kind of environment. You know, there is discussion in the literature about quorum sensing as a possibility of using that as a metric to decide where these microorganisms will populate. But we know from experimental data where they go. But the model needs to be trained in some way, figure out automatically how that will happen given those substrates in that liquid. So that's some research where, again, trying to incorporate that into a reactor design, this is still at the smallest scale. We're still trying to use these tools to design large reactors, and trying to capture this on top of large-scale reactor design, it's computationally challenging. So this is where deep learning can be involved, where you're now saying we can take our lessons learned, and that's the important thing that I'm trying to describe. Because of what we've learned in this process, now we can use these tools to try to bridge that gap, which is a multi-physics, multi-scale problem. So I still believe that there is a role for deep learning, but I want it to be as a partner where humans are still in the loop. So thinking out loud, I want to make a pitch for the entrepreneurial, human-infused deep learning algorithm. Now, why do I say entrepreneurial? Well, NC State just became partners with the Kern Foundation in describing the entrepreneurial mindset. And in their opinion, and we believe it as well, the mindset is based on what they call 3 C's. Developing curiosity, which I have an abundance of, and I enjoy challenging myself that way. Connections, which is really doing your due diligence about what is the literature, how does that influence what you're trying to solve, and really understanding that problem. And then creating value. I think that if we were to infuse deep learning where humans are in the loop with this entrepreneurial mindset, will create a very different paradigm that some companies are already starting to do, with the exception that you have multi-physics that's going to start informing that because of the lessons learned and the curiosity that's built into it. So here's my last pitch. We want to still have interest by the next generation. We wouldn't have been academics if we were not interested in the next generation. So to me, can we use the same trick that my father used in developing problem-solving skills, asking open-ended questions, meeting students where they are in terms of physics, chemistry, mathematics knowledge? I didn't have that kind of reaction when I figured out something. I was just happy if I figured it out. So one of the things that we did in not sharing computational fluid dynamics, but just trying to inspire that next generation, is that we developed a tool that allowed elementary school kids to develop a disinfection reactor. And it was a simple thing. We told them, I said, depending on how much contact that they would have within that reactor, you want to try to put in a reactor with inlets and outlets, design baffles to streamline that flow to try to move through this reactor more efficiently so that it would be disinfected. And so this is kind of outputs that they would create from developing that. And it was already something where they were designing how many baffles that they would put in there. There was a cost every time that they would put a baffle in there. How big that reactor was. There was a cost in the size of that reactor. So there were constraints that they had to decide to do these kinds of models. And they came up with some really fascinating designs. This one was my favorite. But these were inspired by kids who never had tools like these, but they started to understand, and doing some of the simple calculations about the cost in the design, I told them about, well, think about the path that these influent to effluent are taking. Calculate how long that it takes. So they were starting to use physics and some other methodology to compute that, to try to decide how many of these things they should do. And it was really enlightening in seeing that inspiration and the interaction that they would do. And of course, as a prize, when they were in teams of students working on each one of these, that if they were designed a disinfection contactor that had the highest rate of kills, so to speak, I called it kills for simplicity, then they would get a gift card to go to Chick-fil-A. Kids and food, they ate it up, no pun intended. So more designs and things that they did. But again, I enjoyed everything that I did over the years, so much so that curiosity drove everything I did. I'm worried that machine learning might impact that. I hope it doesn't. I hope it doesn't be used incorrectly. I don't think it will, but there's always still a question. And so I've enjoyed everything that I've done. And so with all the sensors that are going everywhere in cars, everything that you can imagine, biosensors, data is abundant. And we're going to have plenty of that. The Internet of Things in terms of smart cities. We need to figure out a way to make sure that we're still learning about what's going on, what's driving some of the way the data is being collected, and using these models in a smart way. So, my pitch in terms of when you're doing these kinds of interactions, I always use this image. Interactions should happen as naturally as rivers are flowing through natural systems, not engineered systems like the one up there. The more the interactions that you have, I like this winding staircase. I use a lot of analogies. I don't know if they're great. But the point is, I believe everything that I have done in working with different collaborators, it's been something that that I have enjoyed. So, transformative engineering solutions or just transformative hairstyles, you decide. Every image here is me. And I really appreciate the time that you have spent with me, and I'm happy to answer any questions that you have.
Okay, so I'm going to play cop, the pointer cop, and there's microphones out there. So if you have questions, start asking. Yeah, Mara. They're going to bring a microphone down to you, I hope. Because what you say is important.
Okay. Well, thank you for the wonderful talk. During your presentation, I couldn't help but recall a class I took at Urbana-Champaign when I was an undergrad, of which I don't think many students do now take anymore, which is engineering ethics. Yeah. And it was very much a writing course and reading course, which I deeply enjoyed. And I think the major aspect was about teaching us to understand how to use engineering and how sometimes it can go awry. And it makes me wonder as if we have to expand on such courses to discuss about machine learning and deep learning. Is it something you would advocate for, to expand these courses to include the ethics of how we use these kinds of tools?
Absolutely. Because the potential for bias, lack of data, and context, is why I was having a discussion today, is important, because if you're not understanding how the data was retrieved, if you're not understanding how it's going to be used, all of these things could be, misinterpreted. And I think, ethics should be a part of all engineering and science. There's a lot of different other things besides just using it for machine learning or deep learning or any kind of data analysis and the challenges associated with that. But I would agree with you wholeheartedly that this is something that should be a part of engineering in general and science in general, not just for modeling's sake and for data analysis sake.
I also have similar question about biases and ethics in modeling. So the model you're building are in the water system. How do you see human bias playing a role in deep machine learning in accuracy of the system or prediction?
Well, particularly if the system is not properly understanding what's driving the process. In other words, we're regulated by what we have to make sure that these processes do, right? Oftentimes these algorithms, they're not transparent, so you don't know what is being incorporated. And the concern is it really understanding and trying to predict and then being transferable to another site? Can it do those kinds of predictions? And so the reason why I'm always pushing mechanistic is because it's grounded through processes that we understand. And so I think these data-driven models should only be incorporated with some kind of physics informed so that it can look at a wide variety of problems and look at it from one place or another. So I think the biggest concern that I have is that people who are designing this, it works at this treatment plant, and then all of a sudden they go to this treatment plant thinking that it's going to work, and it doesn't. And that's because the problems that they're trying to solve and the data that's being collected over here is not completely transferable to over there. So it's just this broad use of just using what you created here and moving it over to another location.
I have many questions, but you've tickled all kinds of things that in my brain. But one thing that I'm thinking about in the examples that you gave, you were able to create situations to look at an observable under a particular condition, right? So you could test empirically, right, the response. So how do we do that when we have these very complex systems where there's multiple drivers, where you can't isolate cause and effect in an observable?
Well,
but then I'm struck by your thing about, starting with the questions. Like if we keep asking the questions, that we might help train ourselves towards thinking about this in the right way. But if we don't have those observables,
I think that's where the power of the data that's being collected to first sort out what is the data telling us. I just don't want it to be used without asking the question why. Right? It's an understanding of what is this pattern in this data that these algorithms are developing. It's mostly correlation. That's causation is a different picture. We have to do different kinds of analysis to really understand causation. But I don't want it to be used and just say, well, we've got this algorithm that figures out all of this without understanding, well, is it really understanding what's going on here? And do we understand why? And that's my biggest claim. And I mean, I just don't want the curiosity about taking the next step in understanding. Now that I see this, let's understand what's going on and seeing what is causing these. That's my whole thesis. Let's not lose the learning that can be gained by allowing these algorithms to tell us something, but then taking the next step and saying, why? So maybe like some kids that keep saying, well, why do I need to do this? Well, why is that? So that's the most curious kid, and you need to foster it. It's like, don't say, because I told you so. Don't stifle that.
I'll take organizer's prerogative before somebody else has a question. So, I have friends that do atmospheric modeling. And these are very complex systems. And what they try to do with this particular individual, young guy is trying to do, is build essentially little atmospheric black boxes that behave like the physics, so that Mauro doesn't have to go crazy in modeling all the details that are going inside the black box. The problem with that is that you don't always capture what the physics of the box is. So, a lot of your work seems to be directed towards that thing, and it's an analog to your question. How do you know when you've captured things well enough that you trust your black box model, your machine learned model?
Well, that's where you go into, if it works and it really captures it, change something about it. Put it in a whole new, different environment. Really test whether or not it does. Because if it really does capture it, it shouldn't matter the location. It shouldn't matter where the observability of whether this model is really capturing the physics, the phenomena that's going on. The moment that you move it to really challenge it, and it still works, maybe you are getting close to what it's really behaving, because probably you want to put it in a totally different environment where the behavior here is very different from where you collected there. If you really want to know if it is something that you understand that process, because it's probably the same process, but you don't really understand all the mechanisms that are involved in that process. And that's what's missing. So I would say we need to challenge those black box algorithms in a way that's meaningful to really understand, does it really capture everything about the process that it says it was trying to capture? And, so, I was talking to somebody today about, going through these kinds of tests that professional engineers do all the time. You got to test this thing and know that you're doing it right. So shouldn't we have the same testing protocol for the people who are creating these algorithms to say, okay, I validate or judge that this process is working well and it's gone through all the testing protocol that makes it efficient.
So let me just quick follow up and then I'll relinquish the mic to whomever. Do you and yours think about the implicit combinatorial explosion? You can't test everything, right? It's kind of like a software testing problem. So, how do folks that do this sort of machine learning in your area think about you can't test everything?
No, and we don't even have the methods to test everything. So that was a problem that we had when looking at UV. We couldn't measure the performance that models were already spitting out. It was already ahead, and we didn't do that. So that's a career in terms of a researcher trying to develop those methods to really get out, okay, is it really measuring what the process is really doing? So no, you can't test everything. Should we go about life trying to test everything? No, but we should keep asking those questions to get closer to being able to judge whether these processes are really mimicking. And so that's testing sufficiently, but not everything. So test efficiently, sufficiently, but not for everything.
Yep. I really appreciated your talk. And what's interesting for me, thinking about this is, there's many a discussion about questioning the ethics associated with machine learning, AI, and so forth, and thinking about ways of doing that in a smarter way and in a more ethical way. But what's fascinating here to me is that, in a sense, you're touching on epistemology in itself, right? Because you're suggesting that, even in the title, that the discovery process is being short-circuited.
Right.
And that we might be doing harm to ourselves,
right,
even by short-circuiting that discovery process, because we're trying to just get what that output is. And I'm just wondering, is there a path here, because I can't think of one right now, where you can still have both, right? The discovery process, but it somehow be enhanced by this magic box or this magic tool that allows us do that in a way that we can choose the pace to be fast or slow or medium without sabotaging the discovery process.
Yeah.
I mean, I know that's more philosophical, but it made me think about that.
Well, it goes back to my crazy idea at the very beginning about it's not just only the data that we should be collecting. We should be thinking about all the questions we should be asking. And, all the frequently asked, I can imagine if somebody were to mine all the questions that humans have asked the internet. How do we do this? How do we do that? If we were to mine all of those questions, I'm just curious the kind of system that would be created just with the questions, so that when something is created, then you unleash this algorithm that asks a billion questions, that it tries to point out either the weaknesses and challenges that data-driven algorithm to see if it's really effective at what it's supposed to do. So I don't know. Again, just thinking out loud, it's just whether or not can we create something that really challenges these tools and vets them in a methodical way to make sure that they're not doing any harm and they are doing the fit for purpose that it's trying to do.
Anyone else?
So 2 questions. One is about maybe there is a field or a career evolving where we find the learning from machine learning and then explore why. Like, why did it come to this outcome? And to then go deeper into that and study after the fact, not necessarily to halt that process in any way. So that's one. Is that happening? And then secondly, take from your the 3 C's. The second one was connecting, and maybe there is also not just multi-physics sort of existing learning going into the process, but also multidisciplinary. So across disciplines, maybe there's some learning from the work that you've done that can also inform how arteries are clogged, and vice versa. So, and maybe machine learning can pick those connections. So those 2 thoughts. I'm just thinking out again.
Yeah. That's why this was appropriately described, right? So coming back to me, I'd like to consider the machine learning, deep learning as a roughing tool. It first goes in, tries to understand the lay of the land because the data that was collected says these are kinds of interactions that we don't initially see. But it's like sending out your for lack of a better word, your minions. Okay, despicable me, I'm despicable. Okay, so sending out your minions that are your algorithms, search the lay of the land. This is what the data is telling you, but then just don't stop there. That's the first step. Now, from that, exercise, there could be a lot of things that happen, and it could be useful in and of itself. But I don't want it to be the end-all, be-all. I want it to be the first thing, maybe, to look at it and see what's happening, but then ask those questions about why that's happened that way. Why did this algorithm say that this is a pattern that came from it? It's got to be. Now, again, I mentioned that there are places where that is not really possible. There really is nothing to really look at in terms of understanding why for that. But then again, if we're using it particularly for protection or other kinds of things that humans are involved, you really want to make sure that it is contextually doing the right kinds of things and not causing more harm than good. So there's got to be tests, there's got to be ways to check that these algorithms are doing these things appropriately. But from a curious type of guy who likes understanding things, I would say I would enjoy using tools like that to really gather more information quickly, as something that's almost there is a field of what there's called a non-targeted, analysis. So you're looking for stuff that you don't know what's already there, and so you're trying to analyze. Well, I could associate machine learning as something as like almost a non-targeted analysis that's helping me understand what the data is telling me. And then I go in to try to figure out, well, why is that? And how did it get there? And all those kinds of things that are involved. So that's why I'm looking at machine learning, is it's almost like a non-targeted analysis.
Okay, I don't see any hands jumping up. So thank you once again.
Thank you very much for attending.